Here we're going to have a problem that's quite a bit different and we got a lot to think about. So let's read the problem carefully. It says a cart has a mass of 1,500 kilograms and is pushed on level ground for 3 meters with a force of 900 newtons, and then it's released at the lip of a hill. How fast is it moving when it rolls down a hill that's 2 meters high? Well, let's see if we can get a picture of what's going on here first. So we've got a hill and a car. And this is obviously a very fancy car that I've drawn here. We're going to push this car for a distance of 3 meters. And then it's going to roll down the hill. And when it gets to the bottom, I know it looks different, but it's the same car, just a little bit later in time. And the question is, how fast is that car going? So we have some things to think about here. So I'm looking for, let's first of all just write down, I want to know the velocity of this car. And we know this hill is also 2 meters high, and you can tell probably not to scale, right? So in order to know how fast the car is going, it's definitely going to be related to the car's energy. So where is the car getting energy from? We know that it's getting pushed. If we never had this car roll down a hill at all and we pushed it, we would be giving it energy. So we're doing some work on the car for a distance of 3 meters, and then the car is going to pick up more energy as it rolls down the hill. And we're going to ignore friction and air resistance in this problem and just go straight out calculation. So I'm going to introduce a new concept in this problem we haven't done yet, and that's that work and energy are the same thing. You use energy to do work. So a simple formula we have that work is equal to force times distance. So let's go ahead and figure out how much energy the car picked up from being pushed along the hill here. Well, do we know the force that was listed here? Well, yeah, we know that the force was 900 newtons, and we know that the distance it was pushed was 3 meters. So this is going to be a pretty easy calculation. Let's go ahead and find out how much energy it got from being pushed. 900 newtons times 3 meters is going to give me 2,700 Newton meters. So that's how much energy it picked up. Now, another thing that I haven't gone with you yet, we'll have talked about it at some point, is that a Newton times a meter equals a joule. Or we can flip that around. A joule is a Newton meter. So this is 2,700 joules. So we know the car has some energy as it gets to the hill, and now it's going to roll down the hill and pick up some more energy. So let's figure out that second part. How much energy does the car get from rolling down the hill? Well, this is clearly going to be gravitational potential energy. So do we have what we need to get that? I know that my formula for gravitational potential energy is mass times gravity times height. Now we need to be careful not to confuse the 3 meter horizontal distance pushed up here with the 2 meter vertical distance that it's going to roll down. And we do know that the height was 2 meters, and we always know that gravity is 9.81 meters per second. Again, for simplicity, we're rounding in these problems to 10. So let's go ahead and find the gravitational energy. So we've got, oh, sorry, I didn't get this one up here. The mass is 1,500 kilograms. So we plug in our 1,500 kilograms, our 10 meters per second squared, and our height. And we're going to get, let's see, 1,500 times 10 times, 2 meters is going to be 30,000 kilogram meters per second squared times meters. That's kilogram meters squared per second squared. That's 30,000 joules. So now we have energy from the work, we have energy from gravity, and now I'm asked to find the velocity. Well, I know the total is going to be 30,000 joules plus those 2,700 joules. That gives me 32,700 joules total energy. Well, fortunately, in one of our previous problems, we know that when you're solving a problem where you've got kinetic energy and velocity, that velocity is equal to the square root of 2 times E over m. Now we can simply plug in the numbers that we have. Square root of 2 times our 32,700 joules divided by the mass of this car, which is 1,500 kilograms. Now I'll spare you all of the unit calculation because we did that in a previous problem. And actually I can just show you one more time here. Joules per kilogram. We know that a joule is a kilogram meter squared per second squared. So I can substitute that in for joule, divide by kilograms. The kilograms cancel. I end up with the square root of meters squared per second squared. I end up with meters per second. So then I can just simply do the numbers here and I end up with 6.6 meters per second. Question was, how fast? I got an answer with units of meters per second. So again, summarizing this problem, we have work done on a horizontal surface that gives it energy, 2,700 joules. It picks up gravitational potential energy converted to kinetic energy, 30,000 joules. Total energy was 32,700, and then I can use the kinetic energy formula to find out that it goes 6.6 meters per second if we ignore air resistance and friction.